Complex numbers and roots. Our objective is to define and use imaginary and complex numbers, as well as solve quadratic equations with complex roots. Why learn this? Complex numbers can be used to describe the zeros of quadratic functions that have no real zeros. Let's start with some vocabulary. An imaginary number is the square root of a negative number. A complex number is a number that can be written in the form a plus bi, where a is the real part and bi is the imaginary part, hence why it's complex. And a complex conjugate is the complex conjugate of any complex number. So whatever the bi was, so the complex piece here, or the imaginary part, that's going to switch. If it was positive, it's now going to be negative. The real part stays the same. Alright, so an imaginary number is the square root of a negative number. Imaginary numbers can be in the form bi, where b is a real number and I is the imaginary unit. The square of an imaginary number is the original negative number. So if you take the square root of -1, that is equivalent to I. So the square root of -2, you can think of that as the square root of -1 times the square root of 2. Well, since the square root of -1 is I, it's I square roots of 2. Well, what if you had the square root of -4? Once again, break it down so that way the negative is no longer there. So you'll have the square root of -1, and then you'll have the square root of 4. Something a little bit easier to deal with. Well, the square root of -1 is I, and the square root of 4 is 2, so 2I. Now, if you are going to square the square root of -1, that's like saying I squared, because the square root of -1 is in fact I. Well, I squared ends up being -1. You can think of it as, what would happen if you said the square root of -1 times the square root of -1? Well, it would just give you -1. Let's practice. So we're going to express each number in terms of I. So we're going to ignore the 3 in front for a little bit, and we're going to deal with what's underneath the square root. We can rewrite the square root of -16 as the square root of -1 times the square root of +16. The square root of -1 is I, and the square root of 16 is 4. So now we have to deal with our 3. Nothing is in this underneath the square root anymore. You took the square root of 16, so now it's just 4. You took the square root of -1, so now it's just I. Therefore, 3 times 4 times I is just 12I. Let's look at one that's a little bit more complex. Once again, we're going to ignore what's outside of the square root for right now, but don't forget about it. So we have the square root of -75. We can take this as the square root of -1 times the square root of 75. Well, unlike 16, 75 is not a perfect square, so we need to separate it out. Well, we can break the square root of 75 into the square root of 25 times the square root of 3. Recall back to Algebra 1 and simplifying things to simplest radical form. Well, we know the square root of -1 is I. The square root of 25 is 5, and we can't really do anything with this square root of 3, so we're just going to kind of leave it as such. Well, once we combine everything together and then go back up and claim what was outside to begin with, we now have -5 square roots of 3 times I. Alright, so solving a quadratic equation with imaginary solutions. There's not much different. If you recall back, when we took the square root to solve, if you remember, we had to say plus or minus, because if you think 3 squared is 9, but negative 3 squared is also 9. So you need to take the plus and minus, just like you do with imaginary solutions. Alright, so we have x equals plus or minus the square root of negative 81. Now we need to simplify the square root of negative 81. So the square root of negative 1 times the square root of 81. Well, that's I, and this is 9. So x equals plus or minus 9i. Let's try this next one. Notice how we were able to jump right to taking the square root on both sides because x squared was by itself. We need to get x squared by itself first before we do anything to b. So let's subtract 75 from both sides, which leaves us with 3x squared equaling negative 75, and then we can divide by 3. So we have x squared equals negative 25. X squared is now by itself, so now we can take the square root. So x equals plus or minus, because once again we're solving and we're using the square root of negative 25. Well, we can break this into the square root of negative 1 times the square root of 25. The square root of negative 1 is I, and the square root of 25 is 5. So therefore, x equals plus or minus 5i. Alright, so now let's look at where complex numbers fall into play. A complex number is a number that can be written in the form a plus bi, where a and b are real numbers, and I equals the square root of negative 1. So together, the 7i makes up the imaginary part, and since the a, or the 3 here, doesn't have any imaginary numbers, it is completely real. So your real numbers are these kinds of things. So negative a half, pi, 0, the square root of 2, negative 9.66666666. Your imaginary numbers are like I, 3i, negative 5i, the square root of negative 7. A complex number takes your real numbers and your imaginary numbers and sticks them together to formulate a complex number. So every complex number has a real part and an imaginary part. Real numbers are complex numbers where b equals 0. Imaginary numbers are complex numbers where a equals 0 and b cannot equal 0. These are sometimes called pure imaginary numbers. Two complex numbers are equal if and only if their real parts are equal and their imaginary parts are equal. So the real parts have to be equal and the imaginary parts have to be equal for complex numbers to be equal. So let's practice with this. So equating two complex numbers. Find the values of x and y that make the equation 3x minus 5i equals 6 minus 10yi true. Just like in what the last slide had stated, your real parts must be true and your imaginary parts must be true. So you're going to set them up separately. So for this one, we'll have 3x equals 6 for the real part, and the imaginary part would be negative 5 equals negative 10y. Real part, imaginary part, they're going to be separate. So in this case, x equals 2, and in this one, y is going to equal 1/2. So these are the two values, so the value of x and y, that are going to make this a true statement. Take a moment and pause the video and try this one on the bottom. When you return, an answer will be revealed. So x would have to equal negative 4, and y, after you reduce it, will have to equal negative 3/10. Alright, so finding complex conjugates. Find each complex conjugate. To start with, make sure you have everything written in a plus bi or a minus bi. Depends on what the sign it is that it starts with. So let's rewrite this so it says keep the sign with the a, so it's minus 15, that's a positive 2i. So to write the complex conjugate, switch the sign of what's in front of bi. So negative 15 minus 2i is the complex conjugate. This one's a little bit nicer. You can technically put in a 0 if you wish, minus our bi. So therefore, it'd be positive bi, which would just be 4i. And that's the complex conjugates. So now let's look at finding complex zeros of quadratic functions. So this will follow for the CP and honors level students or advanced students, since this involves completing the square. So we have x squared minus 2x plus 5. So we can rewrite this as x squared minus 2x plus 5 equals 0. And now we want to move this 5 over. So we have x squared minus 2x equals negative 5, because we want to put something in here and in here. And to do so, we use our b over 2 and then square that. So our b value in this case happens to be negative 2. So we have negative 2 divided by 2 squared. Well, that is simply 1. So we're going to add 1, and whatever you add to one side, you must add to the other. So now we have x squared minus 2x plus 1 equals negative 4. It's a perfect square trinomial. So we have x minus 1 squared equaling negative 4. Take the square root of both sides. So we have x minus 1 equals plus or minus the square root of negative 4. And then we'll add 1 to both sides. So we have x equals 1 plus or minus the square root of negative 4. However, we do have one last step, and I'll change colors for the last step here. One last step. We need to get rid of the fact that we have a negative square root. So now x is going to equal 1 plus or minus, and the square root of 4 is 2, and the square root of negative 1 is I, so plus or minus 2i. Take a moment and pause the video and try this next one on your own. When you return to the video, the answer will be revealed. Alright, so set it equal to 0, then move the 35 to the other side, so that way we can complete the square. B divided by 2, square it, so we're going to be adding 25 to both sides. Now we have x squared plus 10x plus 25 equaling negative 10. We have a perfect square trinomial on the left, so x plus 5 squared equals negative 10. To get rid of the square, we take the square root of both sides. So we're left with x plus 5 equals plus or minus the square root of negative 10. Move the 5 over. We want x by itself. Well, we have one last piece once we have negative 5 plus or minus the square root of negative 10. We don't want a negative square root. So in this case, we can break it down into negative 1 times 10 underneath the square root. The square root of negative 1 is I. But the square root of 10 is already in simplest radical form, so it's simply going to stay. So your end result is negative 5 plus or minus I square roots of 10. And that ends our lesson on complex numbers and roots.